Yes, so recording has started. So good morning once again to all of you. Yeah, so before I start today's class, one important announcement is that the practice paper for this op-amp, that is practice paper 7, has already been shared with you. And you can find the link for that practice paper 7 in our MS Teams. Huh? So please do try to solve the problems given in that practice paper. I will also share with you the solutions. But before I share the solutions, please try to do uh, these things by yourself. Huh? Okay. So in our last class, we have started our discussion. What we are discussing about actually the difference amplifier, right? And we have seen how difference amplifier would look like. It's basically this four resistors connected in this fashion, and to get an output of this form, that is this output to be equal to minus sorry, not this one, final one is this one, right? That is this output. To get an output like this, that is output should be equal to R2 by R1 into V2 minus V1. That is the difference between these two inputs. That is difference between these two inputs. We have to select put one criteria, and that criteria is R4 by R3 is equal to R2 by R1. So if we have this criteria for this, that is R3 by, so see this criteria once again here. It says that R3 by R4 should be equal to R1 by R2. This ratio should be the same. So R1 by R2 should be equal to R3 by R4, right? So if we have that ratio, then that output, in case we have this R1 by R2 is equal to R3 by R4, then in that case we can write output is equal to R2 by R1 into V2 minus V1, right? So that's why it's called the difference amplifier. But here we have seen a couple of issues. For example, if we see for this R in, then we have seen the R in comes out to be the resistances which are connected here, that is R1 and R3, or maybe whatever value you are choosing, that is it's simply the resistance of these two. So that way the input high input resistance that has been offered by a op-amp, that is lost, right? That is one thing. And the other thing is that, so if we have to change the gain, right? So here the differential gain is this one, R2 by R1. So you have to change either R2 or you have to change either R1, or you can change both actually, right? But remember this, due to this criteria, right? Whenever you are changing either R1 or R2, you have to change either R3 or R4 as well. Means at least you have to change, right? So can we do some modifications or some improvement in this difference amplifier, so that by changing one resistance value only, we would be able to vary the gain. And the other thing is, can we do something by which we can get that input impedance or input resistance very high, almost infinite. So to get an input resistance very high, you can suggest that we can add one buffer, right? Yeah, that will solve that input resistance part, but that will not solve the other part. That is, using a change in single resistance, you will not be able to change the gain of this overall circuit. So for that, one circuit can be thought of in this way. So which is called this instrumentation amplifier. Okay. So I think if you notice this part, right? If you notice this part, right? So this part is what? This part is nothing but the difference amplifier. This part is nothing but difference amplifier. That is what we have studied. But we are not only using this thing, but we are also using some additional part with this. But before that, see here the ratios of these resistances are maintained. It is R3, it is R4. So this is also R3, this is R4. So the ratio of these two resistance is equal to ratio of these two resistances, right? So whatever be the voltage here, and voltage means whatever be the voltage difference between these two, V output would be equal to R4 by R3 into the difference of these two voltages, right? Okay. Now let us see what the other changes we have done on this side. So here the input voltage, now we are applying to this op amp. So this is, and what type of amplifier? See, This is if you look for up to this part. Here this V1 is being applied to the non-inverting terminal. So the still it is connected, the negative feedback is been there, right? So negative feedback is still there. For this op-amp also negative feedback is there, right? In between we have connected one resistance which is R1. Now what we are going to do, we will simply connect this output of this op-amp, okay, with the input of this, okay, here, and we will simply connect this with this, right? So as a result, let us see that what is happening. So here it is V1 and the negative feedback is there. This op-amp is ideal. So if this op-amp is ideal, then if this is V1, then this is also be equal to V1, right? You remember that, right? Virtual short concept. So let me use some different color. If I use this one, then it might confuse you. So if this is V1 due to virtual short, this will be also V2. Sorry, V1. If this is V2, again, this is a negative feedback, ideal op-amp. So this is also will be at V2. So V2, V2. Okay. So this is V2, this is V1, right? And if we say like V1 is greater than V2, say V1 is greater than V2, then we will have a current which is flowing from this point and this node to this node, right? And what would be the value of this current? The current value would be equal to, if we say it I1, it would be equal to V1 minus V2 by R1, right? The current which is flowing through this. Okay. Now, if this current is flowing through this, can this current come out of this? No, right? This is an ideal op-amp, so no current can go inside or come out of an op-amp. So this current is not coming from here. So this current has to then flow through this only, right? So this I1 current is flowing through this, right? Similarly, this I1 current cannot go inside this op-amp. So this I1 current has to flow through this, isn't it? Okay. Now see, yeah, do you have any doubt? Okay. Okay. So let us say the potential, okay, of this node is V naught 1. Okay. This V output for this 1. And let us say we denote this as V output 2. Then it shows here there is, yeah, can you still see my screen that I am sharing, because it in between it the image team showed there is some issue.
Yes, sir, the
Yes,
screen is
sir,
visible.
able.
Okay, okay, fine. Okay, so so we have seen what is the current flowing through this, right? Now we know what is the potential of this point. The potential of this point is V1. If this is V1, then this is also is V1, right? So this is V1, and this I1 current is flowing through this. So I1 current will make a drop, right? That we can also find. So we know this, we know the drop. So we can find what is the potential of this point. So that way we can also find what is this V output 1. So what is V output 1? It is nothing but V1 plus I1 R2, isn't it? So it would be V1 plus I1 is V1 minus V2 by R1 into R2, right? Okay. So we are not doing any more manipulation. We can do it if required later on. Similarly, we can also find V output 2, this voltage, right? Because here this is V2, this is plus, this is minus, so it will be V2 minus the voltage drop across this. So it is I1 R2. So it is V2 minus V1 minus V2 by R1 into R2, right? Okay. So we now know what is the input voltage to this difference amplifier, right? And if we know the input voltage of a difference amplifier, then we have seen how to find the output voltage for this difference amplifier. So output voltage of this difference amplifier would be nothing but R4 by R3 into V naught into, it would be V naught 2, right? It would be first V naught 2 minus V naught 1, right? Okay. Now what we have to do, we have to just substitute the value or the expressions that we have got earlier, right? So just substitute the values here. So it is R4 by R3. It is VO2. It is V2 minus V1 minus V2 by R1 into R2. Now this minus, it is V1 minus V1 minus V2 by R1 into R2. Okay, like this we have to do. So this part is also done, right? Then what we have to do, just do a little bit more manipulation here and try to make this expression something like this. Means we would like to take this V2 minus V1 as V2 minus V1 outside. So basically we are trying to do, we are trying to get this V2 minus V1 outside, and from here just do this little manipulation. Okay, it would be 2R2 by R1, right? So if you notice this expression carefully, so what it says is that output voltage of this instrumentation amplifier is equal to R4 by R3 into V2 minus V1. So this see V2 minus V1, this part, okay, if you see this part, and if you see here our earlier yesterday's this one, V output is equal to R2 by R2 by R1 into V2 minus V1. So this part is same, right? What is different here? We have an additional this term here, right? So this term says that it is 1 plus 2R2 by R1. So obviously the gain, overall gain, this has increased compared to the difference amplifier that we have studied yesterday. And what is important here, see this term, this R1 term, right? So by changing only this R1, you can change the overall gain. Right? See where is this R1? This is this R1, right? So you just change this value of R1 and you would be able to change the gain of this amplifier only by changing this resistance value, right? So one of the problem that we have seen for this difference amplifier is solved. Now let us see what about the other problem issue, that is the input impedance issue. Okay, so for that, let us see what is the input resistance, okay, for this source. So this V1 is been directly connected with the non-inverting terminal. So if you see from the input resistance here, so input resistance is here infinite, right? Similarly, V2 is connected directly with the inverting terminal. This op amp is ideal. So here this input resistance is also infinite, right? So both the issues that we had encountered for difference amplifier is been solved. So input resistance is also infinite, means basically very high. That is what we desire, right? Okay. So here what we can do, instead of placing a resistance and or keep on changing this resistance, what you can do, you can use a pot. Pot means potentiometer. Okay, so I think I have shared one video with you. I think prior to, like, before when you have started there, we have discussed what is potentiometer, right? So potentiometer is an this thing is an, it has an basically three terminal. If you connect between these two and rotate this knob, then you would be able to change the resistance between these two terminals, right? And the working principle and what is inside this, I think that has already been discussed in the previous lectures. right? So just use one pot here and you should be able to, by changing the position of this pot knob, you should be able to change the gain of this difference amplifier. Sorry, this instrumentation amplifier. But actually what it is providing, it is basically giving, performing almost the similar operation what you have achieved from the difference amplifier, right? So I hope this part is clear to you. Okay, if so, then we should learn what is common mode rejection ratio. So common mode rejection ratio is an important parameter for any op-amp. In fact, when you purchase an op-amp and then see its data sheet, okay, and its specifications, there one of the most important parameter of an op-amp is this CMR, which is common mode rejection ratio. So what do you stand by this? What do you understand from this common mode rejection ratio? First thing is that let us consider in simple op-amp. So if it is a simple op-amp, if you have this V1, V2, then output is expected to be, right, AOD, that is the open loop differential gain into the difference between these two input, right? It is V2 minus V1, which is basically AOD differential gain into this VID, that is the differential, difference in this input, right? Now, what will happen, say, if this V1 is equal to V2? So if this V1 is equal to V2, then from this you are you will expect that the output will be 0, right? Yeah, that is true for ideal op-amp. Okay, but for practical op-amp, even if these two, if you have shorted and connect to one, similar, maybe means what I am referring to is that something like this. Suppose even if you have connected some voltage like this for this, the output voltage will not be equal to 0. You will get some finite output voltage. So that means even if the common inputs are applied for this between these two terminal, inverting and non-inverting terminal, output voltage does exist, right? So that means the common mode gain is not equal to 0. Okay. So remember that the common mode gain is not equal to 0. Okay. Now we will try to understand this thing, CMRR, with one example here I have mentioned. But before that, so let us understand one more thing from here, that this common mode rejection, right? Okay. So basically, this is there are two terms, right? One is this. This is what? This is the differential gain, right? This is the differential gain. Obviously, it is open loop, right? Then for this, we have also seen the common mode gain that also does exist. It is not actually also 0. So this is common mode gain, right? And if you apply this signal V1 and V2, right, between these two, then the common mode signal is generally defined as V1 plus just the average of these two signal. So this is generally been considered as a common mode signal, okay, for this op amp, right? So this is the common mode signal. This is the gain, right? So if you multiply this common mode gain into the common mode signal, right, then you should be able to find what is the common mode output, means output due to the common mode gain, right? Okay. And typically, these CMRR values are quite high. Right. So it is expressed in dB. Okay, so typically this is expressed in dB. So then what is CMRR? So CMRR is nothing but differential gain by common mode gain. Right, we are putting mod because this gain sometimes might be, depending on which type of amplifier it is using, you are using. So this gain might be positive magnitude, but maybe negative. So that's why we are putting it in mod, right? So CMRR is the ratio of differential gain by the common mode gain, right? If you have to put take it in dB, so this is the actual value. So in dB, then you have to take 20 log mod of AD by ACM, right? So 20 log mod of AD by ACM. Ideally, ACM is ACM is expected to be 0, but practically it is not, right? Practically we does have an finite value of ACM. So that means for an ideal op amp, the CMRR is expected to be very high, right? Okay, so if you have just understood like what is CMRR and how it has been defined and how it has been expressed in dB, let us take one example here for a not differential amplifier. I think I have written here for this difference amplifier. Okay. For this difference amplifier, let us take this example. So here, this is the two input of this difference amplifier. So you can see, check this R1, R1, R2, R2. This ratio has been maintained for both inverting and non-inverting terminal, right? And we have just now completed our discussion on this difference amplifier. So I thought it would be better if we take this example. And suppose here we have a microphone. Okay, here we have a microphone. Somebody is speaking in this microphone, and this microphone, this is the output, electrical output, and we are feeding this output to these two terminals. Okay, and here, so obviously it is some type of signal. So as of now, we are just considering the amplitude. So it is a VID is equal to a 50 millivolt signal, like 50 millivolt signal. And this R2 and R1 has been chosen such that this R2 is equal to 10 times of R1. CMRR of this op amp is defined as 90 dB, and 50 hertz noise is present because these are like, all this here, the powers are coming from the electrical supply that is in our household electrical supply, and that is in 50 hertz, right? That is in 50 hertz sinusoidal signal. So there might be some 50 hertz noise, and this 50 hertz noise, it will be same for both this input as well as this input. So basically then this 50 hertz noise can be considered as that common mode signal, right? And say that amplitude is 5 millivolt. Okay, 5 millivolt, say, just for example, say 5 millivolt. Then we have to find what would be the common mode output voltage. So here the amplitude for the common mode signal, noise signal, is 5 millivolt. So you have to see if the CMRR is 90 dB, then what would be the output voltage due to this common mode noise signal, right? So how to approach, right? So first thing is here, this one, that is CMRR is given as 90 dB, right? So that means 90, those CMRR, we know that this is basically 20 log 20 log of AD by ACM. Here, like AD is positive and ACM is positive, so we are not considering that mod sign here, right? So it is 20 AD log of these two, right? So this is the in dB, right? This is also in dB. So if we now equate these two and try to find, so basically AD by ACM, this is would be equal to log means base 10. So it is 10 to the power 90 by 20, it is 4.5, right? So it is 10 to the power 4.5. That would be equal to AD by ACM. So 10 to the power 4.5, if you calculate, I think it would come around this, right? So this differential gain would be equal to 3, right? So from here, you can see one relation, that the differential gain of this op-amp is 31,622 times of that of this common mode gain, right? So it is pretty high, the differential gain compared to the common mode gain, right? This is one thing. However, we are now interested here to find what is the common mode output voltage. So we should find what is this ACM. So ACM would be equal to AD divided by 31,622. Now what is AD? AD is the differential gain. So differential gain for this, right? For this difference amplifier. So for this difference amplifier, what is the gain? It is nothing but R2 by R1. You remember? Because here V output is equal to R2 by R1 into V2 minus V1. V2 minus V1 is nothing but R2 by, it is VID, right? So it is V output by VID. This is equal to R2 by R1. So here this gain, differential gain is nothing but R2 by R1, right? And here it is given R2 is equal to 10 times of R1, right? So it is basically 10, right? So now we then can find what is the value of this ACM. It is 10 divided by 31,622, right? If you, okay, let us keep it like this. Then here the question is you have to find what is the common mode output signal. So the common mode output signal,
Sir, what is AD here?
AD is the differential gain. Differential gain in a closed loop. This is equal to ACM. Huh. Yeah. Do you have any doubt?
Sir.
Okay. So here into that 5 millivolt, right? 5 millivolt is the magnitude of input signal. So it is basically 10 by 31,622 into 5 millivolt. Right? So if you calculate it, it would come around 1.58 microvolt. Right. So see one thing here, the input, right? It is the common. Let me write it. Common mode input, this magnitude was 5 millivolt, right? And see its output, this output of the signal has now become 1.58 microvolt, right? So you can see here, even though there is a common mode signal applied between these two terminals, this op-amp has the capability to significantly suppress that common mode input, right? And that is because it's very high CMRR of this particular op-amp, right? Due to which it is able to suppress it. Is this clear? Okay, here one more thing. Typical values. Is my handwriting when I'm trying to write it quickly, it's becoming so. Typical values of this CMRR is in the range of 70 to 100 dB, right? So you can understand that how large is this CMRR, right, for practical op-amps. And you want this value to be as high as possible, CMRR. Right. So then if you have understood this part, we can move to the next section, which is the precision half wave rectifier. So this precision half wave rectifier is basically does a job type of like half wave rectifier. So this is the half wave rectifier that we have studied earlier, right? So one sinusoidal signal applied to here, right? Positive half goes, get an output, and negative half you will not get any output, right? Okay. But here this is called the precision half wave rectifier here. So we can see if you just remove this diode, right? If you just remove this diode, right? Then it is basically nothing but a voltage follower. So whatever you give here, the output will follow that voltage, right? We have already studied that. But we have introduced here one diode. So let us see how does this diode help here. So when this Vi is positive, see when this Vi is positive, right? So you think from this perspective that you have some AOD and some, some voltage difference between these two. So whenever this is positive, so this voltage will become positive. So when this is positive, this diode will be forward bias, right? And some current can flow through this diode. Whenever some current can flow through this diode, right? Then this potential, right? This potential, because of this voltage follower nature, right? This potential has to be equal to this. So as soon as this Vi is slightly any value of this positive bias, immediately you will get that output here, right? What will happen to this voltage? Say this voltage is say V internal, INTE or NL, this V internal. So V internal will adjust accordingly such that this voltage should be equal to this voltage and this diode is on. So this, remember here, this V internal will adjust accordingly as you change this voltage so that this diode has to be on and this potential would be equal to this potential. So as a result, what we are seeing, so if you plot this V output versus V input, so from 0 voltage onwards, as you increase this Vi, you will get the output voltage, right? So basically the output voltage would be in this here 145 degree with a slope of 1, right? It will rise, right? However, for our earlier half wave rectifier, what we have seen there is that this diode will only conduct once this input voltage crosses this V gamma, right? Then only this diode can conduct. So we have a gap of this V gamma, right? And after that, it would start this with a slope of 1, right? This is V gamma. This is for this half wave rectifier case, right? So this is conventional half wave rectifier, right? But for precision rectifier, even if the amplitude is smaller than this V gamma, you should be able to rectify that signal, right? Okay. Now let's see what will happen when this Vi become negative. So when this Vi become negative, again from this you can easily guess. So this voltage would now immediately become negative. So when this internal voltage become negative, this diode will not conduct, it will not flow, it will not conduct any current. So this voltage would be fixed to at 0 voltage only. So for Vi less than 0, it is able to block. For Vi greater than 0 or any positive value of Vi, this voltage is able to pass. So that's why it is called this half wave rectifier and precision, because whatever be the amplitude of this Vi, you would be able to rectify it and rectify it fruitfully. Is this part clear to you?
Sir,
Yes.
can you explain how V internal adjusts itself? Means what is exactly happening? I can
What is
analyze by KCL, but
KCL? How are you
yes,
applying KCL?
sir, if we take node V0 ground, then current has to flow through diode from left to right. So
When no, okay, could you please repeat? When we apply?
consider node V0 and ground.
V0 where? This voltage or which voltage?
Output side RL top portion of RL.
Here.
Yes.
This is V0.
Which is VI, yes. V0 is VI, right? Equal to.
V0 is equal to Vi, right?
Now current has to flow downward if VI is positive.
Current has to flow downward if this Vi is positive, right?
Now current cannot flow through, means now we apply KCL, then we will observe that the current has to flow through the left branch. There will be no current in the top branch.
This branch.
Yes.
No, this branch okay. Right now, what we can say is that current will flow through this diode. Okay, this current will flow through this diode. Because
Now,
if this potential is equal to this potential, obviously there will be no current.
no, but there is no resistor, so we cannot.
No. How? See, we have not seen so far now what is inside this. So again, okay, let me put it in this way. Can any current flow from an ideal diode, ideal op-amp? Can any current flow inside or out of an input
Cannot
terminal
flow.
of an op-amp?
It cannot.
It cannot. So from that point of view itself, you cannot say like no current is flowing from this through this.
But we can say that diode is forward biased, right here.
Yeah, diode is forward biased. So it is. So this supply, right? This voltage dependent current source. You remember we have done in our first like op-amp first discussion that op-amp can be thought of an voltage dependent current source. This part output. So this is actually supplying that current.
Okay. Yes.
Okay.
Yes, sir.
Okay. So then can you move to the next part? Okay. Yes, here is another interesting, very interesting thing. That is called this slew rate of an op-amp. Okay. So what do you mean by this slew rate? First, let me write this. Okay. So slew rate is basically maximum rate of change in output voltage of an op-amp, right? So slew rate is defined as maximum rate of change of output voltage of an op-amp. So I think from this definition itself, a couple of things has been clear to you is that, okay, first maybe we will consider one example and then try to come back to this, is unit and what is the typical values of this once again. So here, this is what? This is an, okay, this is what? Which circuit?
Sir, buffer.
Yes. So this is a voltage follower, right? So it is a voltage follower. In this voltage follower, say we are applying here, the input is like this, and say the input is square wave. So we have like couple of square waves. It's the input source. Okay, this has been applied. Okay. And say this is the input. Okay. So here you can see this input is changing from 0 to its peak value all of a sudden, right? Almost instantaneously. But inside this op amp, there are 20 to 30 transistors. So each transistor will have their internal capacitances. So because of which the output voltage cannot change instantaneously as the input is changing. So it will take some time for this output to change. For example, say if this is the input and for a particular value of slew rate, say this output is changing something like this. Okay, like this. Right. So even though like this is an op amp which is and right, this is an op amp and this is an configuration is the voltage follower. And if you are applying this input voltage in square wave, right, you will get an output waveform which is like this. So maybe we can write it. This is the output waveform which will be, which it would look like something. So this is what called this slew means when this is due to the slew rate. Okay. Again, means this is again we slew rate defines as the maximum rate. Obviously, this is not the maximum rate. We are still we have to still define that, right? But say this is for a particular value of this some internal capacitance, right? If this capacitance value or these things are suppose increase, then what will happen? Maybe the might look something like this. Right? The output might something look like this. This is for higher some internal capacitances, right? And say for this case, see still you are getting some type of waveform which is bit distorted but not completely, somewhat distorted, right? And now suppose you have increased the frequency, okay, of this signal, input signal. So input signal frequency increased, so the input signal will now look like this, but the amplitude is constant. See this amplitude here we have 1 2 3, here also 1 2 3, amplitude is constant, but this input frequency has been increased. So now if the same same type of slope has to be maintained here, then see this output would something look like this, right? Right. So you can see even it is the output is not even able to reach its original amplitude for these things, right? So if in you can see, so if you increase this frequency of the input signal, then these things will be an issue, right? You will not be able to, here also it is distorted, but here distortion will significantly increase. Now let us consider the another case. Here we will not increase the frequency, we will keep the frequency as it is. So that means this time period will remain the same. So you can see the time period, right? Time period is from here to here, right? This is the time period t. So that t has now been fixed here. What we are now changing, we are increasing the amplitude. So here the amplitude was 3 unit. Here the amplitude is 1, 2, 3, 4, 5, 5 unit, right? So here wow, the with the, using the same type of rate out change in output rate, the we will get output probably is something like this, right? So so it is very important from this thing that even if you want to reduce the distortion of this output signal, it is important that you keep your eye on the frequency of the signal. At the same time, you will keep your eye on the amplitude of your signal as well. Otherwise, what it can happen, both frequency and amplitude can impact, can affect and make the output signal distorted, right? Okay. So you have understood the what would be the implication of finite slope of change in output, right? So that means the output cannot change beyond this slope, right? So then what would be the unit, okay, of this slew rate? So this is the maximum rate, right? The rate at which it is changing, this is the maximum rate. So this is, then we can also say like this is the slew rate, this because this is the maximum rate. It cannot change like, okay, for one amplifier, for suppose for this green one, for this green one is for a particular one op amp, this red one is for different type of op amp. So for red one, the op amp, that is the op amp 2, this is the slew rate. For green one, that is the op amp 1, if we consider, then for op amp 1, this is the slew rate, right? Okay. Then what would be the unit of this slew rate?
Volt per second.
Volt per time, right? Yes, you are right. So typically this second, if we say, because like, for signal, second is like type of too much time. So typically it has been defined as voltage per microsecond. Okay, so voltage per microsecond. So for NUA 741, you remember NUA 741 is the op-amp IC, right? For which this slew rate is 0.5 volt per microsecond. So what it tells is that if you give 1 microsecond time, then the output can change maximum up to 0.5 volt. Right? Output can change maximum up to, this is the maximum change. It does not mean you have to give always 0.5. All right. Means your output has to be changed a 0.5. Okay. If the output is changing, suppose 0.1 volt per microsecond, fine, no issue. Right. But if your output is expected to change, suppose at 0.6 volt per microsecond, then there will be an issue. So you cannot cross this. You cannot cross this slew rate. Means your output cannot cross this slew rate. Then the signal would be distorted. Right. So this is one important thing which you should know. Right. Then to give one or to find, okay, better to say like here we have type of related, right? This thing that that it is dependent. Okay, that this slew rate or the distortion is dependent on the frequency of the signal. At the same time, it is also dependent on the amplitude of the signal. Right. So let us see that if we can have some type of, obviously, for this type of signal, means for the square wave signal, it is pretty difficult, because here the change in output is almost type of right, the rate of change at this point is almost type of very high. So no op-amp can ideally exactly follow this path. Right. But suppose if you have a sinusoidal signal, right? If you have a sinusoidal signal, then the rate of change of this output is also expected to be quite low, right? So let us see that for this case. Let us say here, this is an amplifier. So obviously from this you can clearly see this is an non-inverting amplifier. This is a non-inverting amplifier. So for this non-inverting amplifier, we have applied an sinusoidal signal with a peak amplitude of this is Vm, right? So basically it is Vm sine of omega t. That is basically we have applied, right? So at this output, what we are expected to get, obviously it is a sinusoidal input. So at this output, we will, and this is an non-inverting, so we will also get a similar type of sinusoidal signal, right? With a higher amplitude, depending on the value. Oh, obviously it is will be higher, right? Because it is 1 plus R2 by R1. So obviously it is higher than, amplitude will be higher than this, right? So let us do this analysis, and from here, and let us see that can we relate the slew rate and this amplitude and frequency of this signal. Okay. So this is the input signal Vm sine of omega t, right? This is the input signal, this part. Right? Then what will be the output? This output would be equal to 1 plus R2 by R1 into the input signal, right? And let us say this total part, like this total part is equal to Vp. Okay. So it is V output equal to Vp sine of omega t. Fine. Okay. By the way, are you with me?
Yes, sir.
Okay. Okay. Fine. So right. So let me write it again. So V output equal to Vp sine of omega t. Right. So what is the then rate of, so slew rate depends on the rate of change of output. So what is the rate of change of output here? Dt. It is Vp, then it is sine of omega t, this omega will come here. So it's V omega, sine will become cos, right? So it is cos of omega t, right? So this is the rate of change. Rate of change of output, right? And we know that rate of change of output should be less than equal to this slew rate, right? So from that way, we can obviously say this omega Vp, right? Cos of omega t should be always less than this slew rate. Let us say we are writing it as SR. Okay, slew rate is S dot R. Okay. Now, what is the maximum value of this? Right, we have to consider the peak value. Peak value will happen when this maximum value, okay, for this term will happen when this cos of omega t is equal to 1, right? So that way maximum value would be omega Vp. So this omega Vp should be less than this slew rate. So omega equal to we can write omega equal to 2 pi f. So this f is generally written as f max. Then Vp, this should be less than this slew rate, right? So basically, see, we have reached to an expression where from which actually we can relate the slew rate with its magnitude as well as this frequency. Okay. So here this frequency, this is the maximum frequency. This maximum frequency is f max, and this f max is called the full power bandwidth frequency. So basically, it is basically denotes the maximum frequency which is limited by the slew rate. Maximum frequency of the output signal, okay, or maximum frequency of the input signal, because that's frequency will not change, right? Input and output. So maximum frequency of the input signal, which is limited by this slew rate. So if we now know this equation, you should be able to find what is the maximum frequency for a particular case, for a particular magnitude, right? So it should be less than this slew rate by 2 pi this Vp, right? So you should be able to relate, okay, what is the maximum frequency of the signal for a particular Vp, or for a particular frequency, what should be the maximum value of peak, like what should be the value of this Vp. But remember here, this Vp is equal to 1 plus R2 by R1 into Vm, right? This is for non-inverting amplifier. If it is for some other amplifier, then you have to also remember what is the value of this Vp, because this gain, right? This gain will change depending on which type of amplifier you are using. So this is
Sir,
thing. Huh.
can you explain this F max part once again? Means what is full power bandwidth frequency? F max part once again, can you explain, sir?
Okay, f max. So basically f max, omega is equal to angular frequency can be related with the linear frequency like this, right? Omega equal to 2 pi f. So this f we are saying this is the maximum frequency. Okay, just denoting it as a maximum frequency, because if you go beyond this frequency for this Vp magnitude, then you will get the distortion.
Means input frequency is fixed, right?
Input frequency is fixed. See here.
So maximum
Input,
possible frequency which we can give so
no.
that
I'm
this relation is.
see here. This is the input frequency is omega, right? Even if you are taking derivative and when you are doing an amplification, no, its frequency is not changing, right? Frequencies remain the same, na? Omega only, right? Only you are doing the manipulation on the magnitude part, na? So the input frequency and output frequency will be the same.
Then what is the notion for F max? Means F is fixed, then what is maximum?
Okay. What is it? So here, so it is something like this. So this is then sine of omega t. You could have also used Vm sine of omega 1 t. You could have also used V of sine of omega 2 of t, where this omega 2 is greater than omega 1 greater than omega, right? And so in that case, you have some limitation on the input frequency as well. So this F max denotes the maximum input frequency that you can supply here.
Okay, then why we are placing a less than equal to sign? Means we can place equal to only.
No, we are saying that, see, never we will make equal to the slew rate, right? We, for the step side, we will always make this rate of change in output is less than slew rate. But this is the type of, critical, right? Boundary. We should not go beyond, it should not be greater than slew rate, right? At maximum, this change in maximum, this one can be equal to slew rate.
Okay,
But
okay,
it
understood,
would,
sir.
right? But it would be better if you make it smaller than this. Okay.
Yes,
Okay.
sir.
So I now actually need just only 2 more minutes. Okay. Just then with almost we will be able to finish it. Now here is this offset voltage. Offset voltages of this op amp. So here, say we have an op amp, right? We connect this to like connect this to op amp and say we have grounded, right? And in that case, what is expected at this output? So at this output, we are expecting that output would also be equal to 0. That is true for ideal op amp. But for practical op amp, if you do this type of test, you will find that output you are having some value of this output, right? So this is called the output DC offset voltage. So for uh, practical op amp, V output is not equal to 0. So that means you have some offset at this output when you have shorted this to input. So this gives rise to output DC offset voltage. So output DC offset voltage is measured when an open loop output uh, means if this input is 0, then when the device is operating at this open loop condition, right? Then what is the value of this voltage? This voltage is the output DC offset voltage, right? This is one of the non-ideality for this practical op amp. Similarly, there is one more thing that is called this input DC offset voltage, and which is defined as the input differential voltage that must be applied to make the open loop amplifier to produce an 0 voltage. So here, that means, so suppose you have grounded this one, and here you are measuring this output voltage, right? Then here you have some variable voltage source, right? So here, this you have to have some input voltage you have to give, okay, to make this output voltage equal to 0, right? To make this output voltage equal to 0. So you keep on changing this voltage and see until and unless this output voltage is equal to 0, right? So this is called this input DC offset voltage. Only these two. Input DC offset voltage. Okay, so only these two part was left, I think. Yeah. Yes. Do you have any doubt?
Sir,
Hmm.
sir, in
Huh.
the op amps, if we have grounded both V1 and V2, and we still have V naught is not equal to 0, sir, does that mean that we have infinite supply of energy?
No, because what you are not considering is that you have also connected V plus and V minus, right? So whatever you are getting is coming from the supply.
Okay, sir.
Sir, in
Like
the
I told you, right? In many cases, we will not show these supply voltages, but If you do not give the supply voltages, these devices will not work.
Yes, sir. Understood, sir.
Sir, in the input DC offset, what about the virtual ground?
What about the
Virtual ground concept? Like if we are
but
varying, but
yes, I understand. Actually, like first thing is that see, virtual ground concept will only come when you have a negative feedback, right?
yes, okay. Sir.
Okay, then we'll begin. Okay, so yeah, I think I forgot to ask. Actually, I should have asked much before. So can we have an extra class for tutorial MOSFET? That MOSFET problem on this Saturday sometime. I want to complete the MOSFET tutorial. That will not take more than half an hour. So I think one day we have meet at around 2:30 or I think 3. Like is it possible 3 to 3:30 this Saturday?
Sir, we have a departmental assimilation program on Saturday from 3 to 5.
3 to 5. Okay, then 2 to 2:30, something like that. So let us then meet this Saturday, okay, 2 to 2:30, and we'll try to finish the MOSFET tutorial part there. Okay. So yeah, for this op-amp tutorial, this tutorial part will definitely will conduct, but I request you to please try to solve the problems that is given in practice paper 7 from op-amp. Okay, then with this we will end our class today. So thank you very much.
Thank you, sir.
Yes, you are welcome.